Alright, so now that we've mastered the basics of static equilibrium and figuring out how to find net torque and net force, let's look at a slightly trickier problem. So this was stolen from OpenStax Physics, which you can go online and look. It's free online textbooks. But this problem says we've got a horse leaning against a wall. They've labeled the center of gravity. They've labeled the force the wall exerts. They've labeled how high the center of gravity is, how far it is from where it's being supported under right here. And so what I'm going to do is I'm going to go ahead and redraw this picture without drawing this picture. Because this is my axis of rotation right here. My lever arm is, well, it would be a straight line from where the force is being applied to right here. I don't really want to deal with that lever arm because I want my forces to be perpendicular, and so I'm going to draw this right triangle that has the vertical component, the horizontal component, and then of course the lever arm R, which is basically not relevant to the whole problem. So what I have is the axis of rotation down here, the center of mass up here. This center of mass is 1.4 meters high. It is 0.35 meters from where it's actually being supported. And then there is another point down here at 1.2 meters, right? That's this horizontal force that's acting this way. So we have this extended body where multiple forces are acting, but the weight is acting at the center of gravity right here. So here's my weight force. The normal force is acting over here where the foot is at. It's being supported. The wall is pushing to the right on this thing, which means there must be a frictional force to the left to keep this thing balanced. So I have a whole bunch of forces. So let's go ahead and write the force and torque conditions for equilibrium. And I might end up drawing this picture again. So the net force, because I have vertical and horizontal forces, I'm going to keep those separate. So the net force in X is equal to the force the wall exerts right here minus the frictional force right there. So this is equal to F wall minus Fs for static friction, and this has to equal 0. And in the y direction, we have two forces. We have the weight force acting at the center of gravity, and we also have the normal force on the horse's foot there. We're not counting this foot since it's kind of kicked up to the side. So net force in y is equal to mg, weight, and that would be negative, plus Fn, and that is also equal to 0. And then we're going to go to the torque conditions of equilibrium. So the net torque. Well, let's look at what forces are causing torque. I'm going to go ahead and let my axis of rotation be the foot because there's two forces there acting at right angles, and that seems like it would make it hard to calculate torques. So no lever arms, no torques. So now I'm going to go ahead and redraw this a little bit exaggerated. There's my axis of rotation. Here's my center of gravity, and here's that weight force, W. Now, we actually know it's perpendicular lever arm because they tell us that this is pulling 0.35 meters from where it's being supported from my axis of rotation. So while I could find this angle and go sine theta, I don't need to because I already have the perpendicular lever arm, this 0.35. So the net torque, let's see, this would be counterclockwise. I'm going to call this one counterclockwise torque then, would be negative 0.35 times 9.8 times 500. That's the weight of the horse, mg. Plus, now I need a clockwise torque to balance that. And the clockwise torque is the force the wall is exerting. But you'll notice it's not exerting it up here on the center of gravity of the horse. It's actually a little bit lower. It's down here. And its lever arm is only 1.2 meters. So if I draw that on this picture, that force is acting right here. And again, I know my vertical lever arm distance. It's this distance. It's 1.2. So I take 1.2 times the force the wall exerts. Now I have my torque conditions of equilibrium, that has to equal 0, and my force conditions of equilibrium. I don't know the force the wall exerts, I don't know the static frictional force. I could find the normal force, and I will be able to find the force the wall exerts over here. So if I take negative 0.35 times 9.8 times 500, I get 4,900 is the weight times 0.35, 1715 Newton meters here, plus 1.2 times the force of the wall, equals 0, and this is negative. So we do a little bit of algebra here, and the force the wall exerts is 1429.2 newtons. Okay? Now what made this tricky is this picture right here where we could have used angles to find Fr sine theta to find our torques, but there's no reason to do that, right? Because the sine of the angle, Fr sine theta, would actually just get us this side of our triangle or this side of our triangle. So we've actually already dealt with our sine theta by dealing with the perpendicular lever arms. So I've got the force the wall exerts is 1,429.2 newtons. Now all I have to do is find the static frictional force. Well, since those two sum to 0, Fs must equal 1429.2. And because mg and Fn sum to 0, Fn must equal the weight of the horse, which is 4,900 newtons. And then we know the static frictional force is equal to Fn times the coefficient of static friction. So we just take 1429.2 divided by 4,900 to get our coefficient of static friction. And if we do that math, we get 0.29. So what makes this problem tricky is we have multiple different forces acting in multiple different angles and multiple different lever arms. And in fact, this right here where we have torques caused by horizontal and vertical forces, that's okay. You still got to classify those as clockwise and counterclockwise, and then we can combine them. Because you'll notice the wall exerts an X force and G exerts a Y force, so I can't combine those forces, but they do exert clockwise and counterclockwise torques, which can be combined. So again, pick your forces, pay attention to sign, label your axis of rotation, and everything has a tendency to work out.